Hey there, Stat 200. This office hour we're going to be talking about hypothesis testing. So this kind of builds on what we were talking about with confidence intervals previously. We're going to kind of formalize it. We're going to almost make it backwards. We're going to make decisions based on whether or not we have a confidence interval that includes a null value. And so when we talk about this decision, we're actually going to assign a different value. We're going to assign p-values. And the p-value, and I'm going to talk about this later, of course, but I want to give a good definition of the p-value right up front, just so we're all on the same page. So, if you understand the concept of a null hypothesis and the alternative hypothesis, now remember, the null hypothesis is the status quo. It means nothing is going on that's special. The alternative hypothesis is usually what a researcher is trying to prove. So, what the p-value is the probability that you get data that you see, that you would get the data that you saw, or data more extreme, given that the null hypothesis is true. So we're going to see a little bit more of that in this office hour. So let's get started. Alright, about 90% of the general population is right-handed. Researchers speculate that artists are less likely to be right-handed than the general population. In a random sample of 100 artists, 83 are right-handed. Which of the following best describes the p-value for the situation? Alright, so remember what I said. P-value is the chance that we see data that we saw, or data more extreme, if the null hypothesis is true. So the null hypothesis means that nothing special is going on. Now in this case, the researcher is talking about artists, right? And he's trying to see if the artists are different from the general population. Now, if the artists are not different from the general population, that means there's no artist effect, right, on handedness. And so, if that's true, then you'd expect that artists, on the whole, the population of artists, would have 90% right-handers and 10% left-handers, right? So that means the null hypothesis is that p equals 90%. So let's write that down. So the null hypothesis here is that p equals 0.90, right? Now our sample, our p hat, is 83 divided by 100, right? You see where I'm getting that? Random sample of 100 artists, 83 are right-handed. 83 right-handed out of 100. So now we have that. That's basically what's been told to us. This is the null hypothesis. This is what we received. Actually, we know also what the alternative hypothesis is. A researcher speculates that artists are less likely. This is almost always going to be your alternative hypothesis. Whatever the researcher is speculating, alternative hypothesis. So let's write that too. Most of the time we're going to see it look like this. HA. In this case, it's going to be that P is less than 0.90. Okay? Alright, so that's all the information we have. Now the answers are as follows. Which of the following best describes the p-value for this situation? The probability that the population proportion of artists who are right-handed is 0.9. No, that's not the p-value. That's actually nothing in the context of this problem. Let's keep going. The probability that the population proportion of artists who are right-handed is 0.83. Again, no. They're trying to confuse you. See, these are the null value and the sample value, right? These are those two values that we have here. That's not the same as the p-value. Okay, so now we have the probability that the sample proportion would be as small as 0.83 or even smaller if the population proportion of artists who are right-handed is actually 0.9. So, if you can follow along with what I said before, the null hypothesis is the chance that you have data that you saw or data more extreme given that the null hypothesis is true. So let's work backwards. Given that the null hypothesis is true. So this says if the population proportion of artists who are right-handed is actually 0.9. Well, that's the null hypothesis. That says given the null hypothesis is true. And here we have the data that we saw, p hat of 0.83, or even smaller. Remember I said even more extreme, or data more extreme? So this is the answer right here. It matches up very, very well with the definition I gave. But let's go to the next answer option, just to show you why that one's wrong. So this one says the probability that the population proportion of artists who are right-handed is less than 0.9, given that the sample proportion is 0.83. This is kind of making it backwards. Right here we say if the population proportion is actually 0.9, and this says given that the sample proportion is 0.83. It's really easy to confuse these two, right? The probability that the population proportion of artists who are right-handed is less than 0.9. This is making it backwards. This is basically saying this is our null hypothesis and this is the alternative. But that doesn't make any sense in this context. Okay? So when you think of the p-value in terms of hypotheses, the thing that's always given, the thing that's always expected to be true, right? It'll say if this is true or given that this is true, is the null hypothesis. And then we're going to talk about the probability that you see the sample data or data more extreme. I know I've taken a long time on this problem, but it's a very important concept. Just keep that in mind. Further questions, just send me an email. All right, moving on, next one. A hypothesis test for a population proportion p is given below. Null hypothesis p is equal to 0.4. Alternative hypothesis p is less than 0.4. Okay. Use the standard normal table to calculate your p-value for this hypothesis test for a z-statistic equal to 2. Okay. Now, very important. We're looking at this table, which means we're trying to find area in the normal curve that corresponds to this probability. Now, whenever you see an alternative hypothesis that is less than, that means whatever our value is, we're going to be looking at the area to the left of it. So z is 2, right? We're saying z is equal to 2. So what we're looking for here is we're looking for the area to the left, because this is what we call a one-sided hypothesis. This doesn't say not equal, it says less than. Another example of a one-sided hypothesis, if this had said instead greater than. So, we've established that the standard score is 2. We're going to be looking for the probability to the left, and that's great actually, because this table only gives probabilities to the left of the z-score. Okay, so what are we going to do? You'll notice that on this side, all the numbers have negatives in front of them, but our z-statistic is positive, so we're not going to use this side at all. This side has positive values. That's good. That's what we want. So it's 2.00, right? So this gives the ones place and the tenths place. This header up here of these columns gives the hundredths place. Now you notice that the ones place here is a 2, the tenths place is a 0, and the hundredths place is a 0. So we're going to just go here. 2.0, 0. 0.9772. Okay? So that's our answer, 0.9772. It's actually right there. And it might seem maybe a little too easy because you just looked it straight up. Many people are thrown off because this is a less than hypothesis, but the z-statistic is actually on the positive side. Usually when we see these types of less than hypotheses, the z-score will be somewhere down here. It'll usually be to the left of the mean, but in this case it's to the right, so it's super unlikely that p is less than 0.4. Very, very unlikely, because we got a sample proportion that's actually higher than the null value. Very unusual, and that's something that trips people up. Alright, let's move on. A counselor wants to show that for men who are married by the time they are 30, mu equals the average age when the men are married is not 21 years old. A random sample of 10 men who were married by age 30 showed an average age of marriage of 22.2 years, with a sample standard deviation of 1.9 years. Assume that the age at which this population of men gets married for the first time is normally distributed. That's a key thing. So pay attention that we're saying this. Assume the population is normally distributed. Now, using the t-value and a significance level of a equals 0.05, which of the following is an appropriate conclusion? Right. So, let's just break down what we know. Now remember, the three answer options we have are: the results are statistically significant, average age appears to be greater than 21. The results are statistically significant, so the average appears to be less than 21. The results are not statistically significant, so there is not enough evidence to conclude the average age is different from 21. Now remember, we decide whether something is statistically significant or not based on whether or not the p-value is less than the significance level. In this case, it's 0.05, and that's a very common significance level. So how do we find it? Well, we take our sample average, which is 22.2. Oopsie. Hold on. Sorry about that. Let's get rid of that. Let's make this a little bit neater. Here we go. 22.2 minus our null value. So, counselor wants to show that for men who are married by the time they are 30, mu equals the average age of men when the men who are married is not 21 years old. So he's trying to show that it's not 21. Now remember, what the researcher is trying to show is not true is usually the null hypothesis. Now the null value here associated with the null hypothesis is 21. Now you'll notice that he didn't say it's greater than 21 or less than 21, he just says it's not 21. So this is actually a two-sided hypothesis test. Let's write these two hypotheses down. Null hypothesis is that mu, the population average age, is equal to 21. And the alternative hypothesis, mu, average age, is not equal to 21. That's what we have here. And this is something we call a two-sided hypothesis test, right? Because it could be less than 21 or greater than. Now, back to calculating what we need to calculate. We're going to calculate the t-value, the t-score, for use of the t-table. We can also call it a test statistic. So we take our sample value, we subtract our null value, and then we're going to divide by what? Well, we're going to divide by our sample standard deviation, 1.9, divided by square root of 10. Why do I do that? Well, if you are thinking about what we're trying to find here, we're talking about the sample mean. We're not looking at individual values. We're talking about an average age. We're talking about averages here and here. When we talk about averages, we're going to be talking about sampling distributions rather than individual distributions. Now, if you remember what we talked about for sampling distributions, this means that we need to divide the standard deviation for the population, or the sample, by the square root of the sample size, because we're talking about averages, not individuals. Okay? So, we can plug this all in. I'm going to simplify this a little first. So 22.2 minus 21 is 1.2, divided by 1.9, divided by the square root of 10. Now it's important to note that divided by square root of 10 is in the denominator. So we can go to our calculator, and we'll plug this value or these values in right here. So go ahead, I'm going to pause it. Alright, did you find it? If you got it correct, the answer should be approximately 1.99, or you can say approximately 2. Now, what we need to decide here is with that kind of value of the test statistic, are we going to get statistical significance? So let's look. Now on this table you'll notice we have a bunch of columns. First one is DF. DF stands for degrees of freedom. And there are a lot of ways to explain this, but basically the degrees of freedom tell us how much weight we're going to give our experimental data here. And that's affected by the number of people who are in our sample. The degrees of freedom are the sample size minus 1. So in this case, the df is 10 minus 1, which is 9. So we're only going to restrict ourselves to looking in this row here. No. We're looking at confidence levels, right? Confidence level is basically 1 minus the alpha value. Now our alpha value was 0.05, which is the same as 5%, which means our confidence level is 1 minus 5%, or 100% minus 5%, which is 95. Basically what we're going to be doing here is we're looking at our value from this, and if our test statistic has an absolute value greater than that value, then it is statistically significant. Now in this case, you'll see the value we're going to compare against is 2.262. Now we have a test statistic with a value of approximately 2, which is not greater than that number. So what that means is, in this case, we don't have statistical significance. Scrolling up, this actually makes our job very easy. There are only 3 options, and the only option that is not statistically significant is this one. The results are not statistically significant. There is not enough evidence to conclude the average age is different from 21. Okay? Now, one more thing, now that I've pointed out the answer, to note. You're looking at a two-sided hypothesis test. This could have gotten you in trouble, because if you were thinking it's a one-sided hypothesis test, you would actually be looking at a confidence level a little bit higher than 95%. You might have gone to 98%. And if you would have done that, you may have found that you would have an easier time. Or I'm sorry, I went the wrong direction. You might have used the right tail probability of 0.5. If you had done that, you would have compared it to this value, concluded statistical significance, and then you would have said it was greater than 21. But because this is a two-sided hypothesis test, because right here it says it's not 21 years old, not as greater than, not as less than, is not. That's why you're going to use the right tail probability of 0.025 in either tail. This is the confidence level that is associated with a two-sided hypothesis test. Very important for you to remember that. If you have further questions on that one, I understand it's a complicated process. Please don't hesitate to send me an email. But for the sake of time, let's move on. A hypothesis test gives a p-value of 0.30. If the significance level is 0.05, the results are said to be statistically or not statistically significant. So let's decide, right? We were talking about that before. We compare our significance level to our p-value. If our p-value is less than our statistical significance level, then it is statistically significant. If it's greater than, then it's not. Right? Now, a red herring, I don't know if that's the correct term in this case, but something that's meant to throw you off here would be practical significance. Now, when you're given a p-value and a significance level, you can't make any kind of judgment about practical significance. Practical significance is basically, well, for example, say you have a sample that's huge. This happens a lot, actually, in very large samples. You have p-values that are just really, really small. So you might get a p-value that's, 1 times 10 to the negative 8, for example. But you might look at the baseline risk and the increased risk, which we're going to talk about in a few chapters, and you'll find that the difference is actually not that much. This happens all the time with pharmaceutical testing. Some drug may be found to be statistically significant, in a, say a trial with thousands of people. But when you look at how much it actually prevents a certain disease, it's like barely anything compared to either not taking that drug or taking the current leading drug. It might just be, a less than 1/100% change in risk. So that's what practical significance is. But you can't even talk about that. You don't know the context of the problem. You don't know anything but the p-value and the alpha level. And as I said, if the p-value is greater than the alpha level, it's not statistically significant. Okay? So that's how it works. That's all I've got for you this week. If you have any questions, please feel free to send me an email. I hope you guys are noticing a little bit of the analog between this and confidence intervals. Now with confidence intervals, we were saying, the confidence interval does not include the null value. Therefore, we're going to say, it's extremely unlikely that the actual population parameter has this value because it's outside the confidence interval. That's the same as having a p-value that's less than our significance level. That's just another way to think of it. All right, just something to think about. Thanks for watching. Good luck on those quizzes. Let me know if you have any questions.